right, so I want you to take a look at your lab. And let me find this to throw up there for you. Make it bigger. All right, couple of things that as you look at your lab, and certainly you know, ladies and gentlemen, that I graded the top one because I told you that and you picked which one you wanted me to grade. So a couple of things that I was looking for, and I'm going to point out to you that I was looking for points. First of all, for the data, I was looking if you actually had an appropriately made data table. What is data, what is not? And is density data? No. There was no density-o-meter that we had in the room, so you couldn't put that in there. Did we have a volume measurer for the metal or red cylinder? Was there like something you put in and it read the volume out directly for you? No, so that's not data. Now, many of you, for example, with the metal cylinder, you did it by water displacement. So you took an initial volume of the water, you dropped it in, and then you took a final volume of the water. That's data. But looking at saying that the volume directly, that is not data. All right, so taking a look now at this graph, I looked at your graph here, and it should have been a mass versus volume graph here. You had your best fit line that you should have drawn here for the metal cylinder. And then there are a bunch of other lines you should have. You should have had the water, the red cylinder, ethanol, and styrofoam in that order. Some of you found the red cylinder's density to be precariously close to water, or in some cases, you may have found that the red cylinder line was actually in between the metal cylinder and water. It shouldn't have been. So it probably went to question 5. Question 5 asked, how did you find the volume of the red cylinder? And I think every single person in here found it by water displacement. So I think every single person in here got a note from me saying, it floats, because you can't find the volume by water displacement of something that floats, because you're only finding the volume of what is submerged. Jeremy? So you got the volume of the red cylinder and the tip of your pencil. That would be better. Not perfect, but better. Nobody told me they did that, though. Trevor?
What if it went down and got launched diagonally so it didn't actually look like it was floating at all?
I think you made that up.
No, I'm not. It was actually diagonal and didn't go upwards.
How did that happen? It floats.
Because we pushed it down into it and it got stuck diagonally.
Well, then it would work, I guess. Strange. Yeah, I've never ever heard that ever. So how else, other than what Trevor just mentioned, how else could you have found the volume of the red cylinder knowing that you shouldn't do it via water displacement? Kate? Oh, we could have done a little measuring. Maybe the diameter, maybe the height, you know, pi r squared h, right? So that could have worked. Brandon?
So I didn't know that you can't, take, volume off something that floats. So, but we got marked off twice for it, also on the graph, because our graph was correct based on our data.
So you lost 1.5 points then as a result. I'm okay with that. And guess what? Those of you who learned that same lesson today, that you can't take water displacement of an object that floats, count that as you learned something today. All right, moving on. Density here. 2.70 grams per milliliter. I think almost everyone found, determined it was aluminum. There's a table in your book. You can consult the density. But most of your calculations turned out to be pretty close to that. And really important thing here, slope of this mass versus volume graph is the density. Because since slope here, up here again, is rise over run, well, that's rise is mass. Run is volume, so that's mass over volume. So your slope is your density. So when I look at this graph and I look at the red cylinder compared to water, how do I know just by looking that the red cylinder is going to float? Yep. Okay, it's less dense. It has a smaller slope. So it's less dense. And if I compare that, like this metal cylinder here, the metal cylinder has a much greater slope than water does. So it's going to sink. So we can tell by the slope of that graph, the bigger the slope, the bigger the density there. Okay? Questions on that? Brandon?
So we pretty much got a similar grade across because a lot of these problems happen in those years, right?
It happened to most of you for that particular one. This was actually very unusual because usually most years I have at least half the class measure it the other way, but I think someone like saw one person do it and then you all did it that way. I'm not sure what happened in this particular class. Even last period I had people measuring it. Well, you could have done the metal cylinder with a ruler too. I mean, you all decided to do. I didn't tell you how to measure that at all. But, it is what it is. Okay, so this is a little bit about density. Now, what I want to switch to here for a moment, and I'm going to have you go ahead and throw this into your notes. Yeah, you too. In this lab, you measured the density of solids, the two cylinders. You measured the density of a liquid, the ethanol. You didn't measure water. You had to put it on the graph, but you were able to put it on the graph because you knew its density. Same with the styrofoam sphere. Like you calculated the density, and if I actually go back to that original thing, and this is exaggerated, but your point would have been way out here somewhere, but you were able to put it on. If you can figure out the density, you could have picked a volume here and figured out what the mass would have been, and then drawn a line. And the other thing I did want to mention is, why should they all intersect the origin? Schaefer? Yeah, when the volume is 0, the mass has to be 0. Those of you who had lines that intersected the y and the x-axis at a point other than the origin, please think about what that meant. That when it's 10 milliliters, it has 0 mass. Or when it's 0 milliliters, it still weighs 5 grams. That's what some of your graphs told me. So it had to intersect the origin there. All right. Back to this that I was throwing up here. I want to show you just quickly about finding the density of a gas, which of course is a little bit harder because it's not like you can stick it in a balloon and put it on your balance, especially if it's like helium. Try to mass a helium balloon. That's kind of fun. But then it would weigh less as the balloon, buoyancy pulled up. It would be just a problem. So I'm going to show you. So there are some more creative ways, perhaps, to find the density of a gas. I'm going to show you one today of how to find that density of a gas. There are certainly other more sophisticated ways to do it than what I'm about to show you, but I don't have all the sophisticated tools necessarily. But with just 3 pieces of data, I can go ahead and do that. All right. I need somebody who's feeling artistic. Anyone? Because we're taping this for Michelle and Matt. You feel it? Well, can you draw? I'm going to do a little demo. I want you to just draw the picture of kind of what I'm setting up. You can even come back here if you don't mind. That way they can have a picture of what's going on. I hope they watch this after all. You could just draw it over here, like a little picture of the setup. I'll show you exactly what I do. Okay. All right. So, can you turn on the lights? Here's what you can start drawing, Kate. This little flask is going to be attached to this. Okay. I haven't done it yet, but you can start drawing it.
Wait, I need a black.
Already working on drawing this equipment, fancy stuff. All right, so what I have right here is I have a flask with a sidearm, a stopper that's going to go in it. It's filled with a little bit of water, and our good friend Alka-Seltzer. We're going to use that as forming our gas. What gas is given off by Alka-Seltzer? Do you remember? Carbon dioxide. So if you look at that very first thing, it says the mass of the flask, water, stopper, and water before the reaction. So I'm actually going to take a mass. I'm going to put the Alka-Seltzer right up here because I don't want to get in the water. So I'm going to go over to the balance, and I'm going to take a mass of this. You guys write down what I say. I won't remember. Or Kate, maybe you can record it too. All right, here's the first mass. It's 302.343 grams. 302.34. I already forgot what that last number.
343 grams.
Okay, good. 343 grams.
That's the mass of the flask.
Perfect. Now, I gotta collect the gas and I need to have a volume of it. And so this bin that I'm gonna show you is actually designed a little bit for collecting gases. It has a hole in the bottom and it has a tubing that comes out of it, which I am going to attach to the side arm of this flask, like she has drawn up there for you. But in order to do this, I'm going to collect the volume of the gas via water displacement, just like you guys did for the cylinders. But we're going to do this using what I like to call the bathtub trick. You know how when you're a little kid, you're playing in the bathtub, sometimes the best toys were just cups? Because you could like fill them up and then you turn them upside down, and if you did it just right, the water would stay in the cup. You know what I'm talking about?
Yeah.
Those of you who have no idea, go home and play with cups. You can do it in the bathtub if you would like. All right, so what I am going to do, first let me hook up my sidearm flask here.
Why doesn't it fall through the hole in the bottom?
Why doesn't what fall
You
through?
said there's a hole in the
Oh,
bottom.
because this tubing is actually connected to that in the bottom. I love the artisticness. It's fabulous. So there's water in the bin, just floating on top. I am going to fill up this graduated cylinder all the way to the tippy top. And I'm going to turn it over. I know, sometimes it does that. Isn't it annoying? I'm going to flip it over so that I keep all of the water in the graduated cylinder.
And that's why they're numbered upside down sometimes.
Sometimes.
It's really annoying, but I guess it's just...
So I'm going to use a little piece of paper towel. And I'll flip it over so that there are no air bubbles in there. It's completely filled with water. And I'm going to put that over the hole so that when I drop the Alka-Seltzer in the container, it's going to start bubbling and go through here and bubble up into my graduated cylinder. And I'll collect the gas. So that's my job. I'll do that. And I am going to flip. Darn, it keeps disappearing. All right, good job. So I put that in, and it starts to react. And you can see right away that I start to get some bubbles because the Alka-Seltzer is reacting with the water. I'm just going to hold this because I'm worried I'm going to knock it over. I'm going to give it a swirl because I'd like it to dissolve. So it's just bubbling away, kind of slowly. Why do I have the water where? In here? It's the only way to keep the water in the graduated cylinder is to have it sitting, the mouth of it sitting in water. If I simply flipped it over, all the water would come rushing out. Giving it a swirl, make it go a little faster, help it dissolve quicker. It's almost all dissolved. There's still a little tiny piece there. We're waiting for it. It's mostly done. Sure, but there was gas there to start with. So in terms of the volume of gas, it's actually going to be negated. All right, it looks like it is done.
The gas in the graduated cylinder isn't necessarily carbon dioxide gas. It's mostly
It isn't, but and when we get to the gas chapter, we'll realize it won't matter. No, it won't matter. All right, so I'm going to go ahead and measure the volume of the gas, which is, let's see, 36.6 milliliters. 36.6 milliliters is my volume of gas collected. All right, now I'm going to go take a final mass. Did you guys write that down? Okay. Tell Kate, she'll write it down.
36.6
36.6 milliliters, remember what I said?
Yep.
fabulous. I'm so thankful that you did that. Should we draw that? No, this is really because Michelle and Matt aren't here and they won't know what we did. Go ahead right now and calculate, pull out a calculator, calculate the density of that gas. If I would have drawn that picture, it would have been way uglier.
That's 0.56 grams divided by.
I'll get my calculator too.
Let's do some long division.
All right, so you get like 0.056 grams. Did I not subtract that correctly? I did? Okay. Too many people said no. Just the mass, right? That's the grams of the gas that was not the density, just the grams. That was the mass of the gas that was lost, because everything else stayed in the flask. And then I can divide it by my volume, 36.6 milliliters. I don't know what that turns out to be, 36.6. And I get a density of 0.00, how many significant figures am I allowed? 2. 0.0015. Did you guys get that as well? Or is it just me? Okay. That is a very tiny density, but it's a gas. It should be really, really not very dense. Right? That would make sense. It bubbles and floats in water, right? That's the whole idea of how I was able to collect it that way. So I just wanted you to see that certainly you can have a density of a gas as well. Just sort of a creative way to measure one, using some equipment that we had at hand. Now, was that a chemical or a physical change, that Alka-Seltzer? Chemical change. So we're going to use that to kind of segue for a moment, just to jump back to physical and chemical changes, because we didn't talk about them in great detail. So I want to just for a moment mention the idea of physical changes versus chemical changes. Well, we just never really finished our discussion. We ran out of time. So I just want to make sure we hit it. Trevor?
And just don't forget the atoms, elements, and matter.
Well, yeah, that's the bulk of chapter 3, atoms, elements, matter, mixtures. So yes, absolutely it will be. All right, so here's the key question when you're dealing with physical or chemical changes. The question you really, really want to ask yourself is it the same substance after the change occurs? Because if the answer is yes, it is the same substance, then it's a physical change. And if the answer is no, it's not the same substance, then we're talking about a chemical change. And so what I want to do is I want to show you a demo right now that kind of brings up a variety of those changes that we find in a chemical change. So let me pause this for these guys. What I want to do then right now is I want to look at, you saw this demo that I showed you, and I want to come up with as many signs of a chemical change as you saw. I'm going to use signs of a chemical triangle. That means delta, which means change in science. So what are some of the signs of a chemical change that you saw back there? What are some of them? Kaylin? Okay, so there was a release of energy. Now how did, oh, and I never showed you what it looks like. So I got to go grab that. Release of energy. What did you see that told you there was a release of energy? Like sparks, right? Light, right? One thing I will tell you, because now it's cool enough that I can go back and touch it, I can come and show you what it looks like. So that does tell you something else. Yep. So that alone tells you what's another sign of a chemical change. Yeah, so a temperature change is a sign. And so now it certainly looks a lot different. It's not homogeneous. Okay, so I've heard a temperature change, because this definitely got hotter. Which, as you look at this, you can see there was also a color change, because it's not that white and gray stuff mixed together anymore, right? Looks kind of yucky. Well, that's still, so we had a release of energy in the form of light. There was a color change. Yes, those are both, yeah. Temperature change, which doesn't have to be a release of energy. So it can be a change in energy away. Temperature change, which is also falling under an energy change. What else? Trevor? So so there were these fumes coming out. So that tells you what was formed in that reaction. A gas. So we had a formation of a gas. Now there's one I didn't allow you to experience. Smell. I can guarantee you that had a smell. Okay? Mostly like smoke, but any kind of an odor change. Any kind of an odor change is often a sign of a chemical change. So notice one demo, we hit all of these things. There's really only one other sign of a chemical change that we couldn't see in this one because it didn't apply to this particular reaction, and that is the formation of a precipitate. Anyone know what a precipitate is? And I don't mean rain. Kate? No. Not quite. Not quite. Tia? Yeah, it's a solid that forms at the bottom. If you take like two solutions and you pour them together and you get a solid that forms and falls to the bottom, that's what a precipitate is a solid that forms and falls to the bottom. Michael? Well, it doesn't have to be, but if it was a liquid, it'd be less obvious. And so seeing a solid is easier to see, and that's a sign. The gas is not a precipitate, it is a gas. A precipitate by nature must fall down, like the term precipitation for rain. That could fall down, but we wouldn't be able to see it very well. Brandon.
When I was at, I think Loyola Hospital for Body Trek, we went to an exhibition on technologies used to like cure stroke and stuff like that.
Yep.
And one of the technologies they used was they had.
All right. Now, here's the thing, you guys. I mentioned these things, but what we have to remember is these are only signs of a chemical change. If you see this, there's a good possibility it's a chemical change, but the most important question is this one. Is it the same substance after the change occurs? We talked about, I think yesterday, when water boils, it forms a gas, right? Chemical change, formation of a gas? No, that's a physical change because you have the same substance. You took blue water and yellow water and you poured it together and you got green water. Color change, physical change, right? No. Okay? So I just want you to be aware of, you've got to always use these signs of a chemical change in the context of this question. Is it the same substance? So if you know something like it's water boiling, well, that's not going to be a chemical change. Trevor?
So if you're not given the information that it is the same or different substance, can you assume it's a chemical change? If it's like
If you,
instead start spitting out sparks.
if you start seeing more than one of these, it probably is. But looking at just one in the context of not knowing anything else, if you're not told other stuff, I guess you could probably assume it to be chemical, but you could be wrong. You could be wrong. All right, one other thing I want to show you today. Let's find it. Let's see. All right. You do not have to draw this picture I have in here. This is solely for the people who are not here. Well, we're going to play cooking show for a moment because I have like 6 minutes to accomplish this, which takes 30. So I'm going to, pull out the completed product, and it's already going to be cold, but that's okay. So what I have got, or what I'm going to show you, is just sort of a little bit of problem solving I want you to think about. And I have this black, pure substance. Okay? We actually would take a mask. I'm not going to. I'm going to make up a mass. I'm going to pretend I have 6 grams of this black pure substance. Yes, I totally made that up. Now, I've got this contraption back here that I have drawn kind of up here on the screen. But what I have is I have a small amount of that black substance in the bottom of a test tube. 6 grams, according to me. And then I have another tube with a glass tubing that is attached to my gas jet that I am actually going to put inside of here. And I'm going to heat this in 2 places. I am going to heat it in the bottom with a Bunsen burner. That's what that one little picture is, in case you can't interpret my picture. So I'm going to start that. And then I am also going to put methane down here, and I'm going to light that on fire. It looks cool, so I got to show it to you, even though we're just, not going to take full. This methane is natural gas. That's what comes out of here. So this is the picture. Do you see how it sort of, I know it's not turned the same way, but this is the picture. So what I'm doing is I'm going to take this black powder, and for the sake of our cooking show, we're going to say 30 minutes later. As you can see, I don't have 30 minutes. We're going to heat this for 30 minutes. We could wait. So we'll pretend 30 minutes have passed. And so this is heating and heating and heating. And what I'm going to do is I'm going to turn off the flame, and I'm going to pretend like I took a mass of the stuff that's left. And I'm going to show you what that looks like. So I'm going to go ahead and turn that off and turn this off. There's still a flame there. There, it's gone. And so then I take this black powder, which I can't touch it now because it's actually hot. But I take this stuff out, and I dump it in a dish, and I take a mass of what remains in the dish. And the mass of what remains in the dish is 5 grams. And I had a black powder originally, and this is what remains. It's not cold. Okay, so this is, so you see where it says observations? You can make an observation of what it looks like right now. So I had a black powder is what I started with. This is what I ended with. So those of you who've seen it, you might notice it looks a little shiny. I don't know, what color do you guys want to call that? Copper, brown, reddish.
Peanut. It looks like a seed. I want to eat it.
Brownish, orangish, shiny. So here's my question to you that I want you to take 15 seconds with your partner and determine. It was a pure substance, which means it was either an element or a compound. Take, 20 seconds with your partner and decide, was it an element or a compound based on the information I provided? What do we say, element or compound? Do you all say that? I agree with you. Now, can someone tell me, so this black substance was a compound, why do you say that? Why do you say that? Michael? Yeah, if you heat an element up, it's not going to change color and have a chemical change. If an element changes color, it's probably because something else got added to it, right? To make a compound, what would happen to the mass then? If something got added to it, it would go up. So the fact that, hey, we lost mass, there was a chemical change and we lost mass, it must have lost something out of here, right? Well, can an element lose something out of there? No, but a compound could. Kate?
So you're saying in all, I don't even know how many elements there are, but if you heated up every single one, none of them would have a like.
Not unless they had a chemical reaction, in which case they would have to react with something else. and then they would get heavier because they would have added something to them. Right? Michael?
What if the black powder reacted with the air, with the methane,
And then lost some.
and then like a product was gas? And then
Well, sure, we wouldn't know that. I can tell you that that wasn't what happened. What was that? What was that that was left over? The stuff in my hand. Could you tell by looking? It was copper. It was copper, the element. I know for sure it's copper, yes, because I started with copper oxide. Oh, thank you. Yeah. Yeah. I don't know if you're right. I owe you a half a point back. I will give that to you. Can I hold on? Oh no, you know what? Let me.